talk to us today about demons do not die. Okay, I will leave this for him to explain. Okay, but it's going to be a very, very interesting talk. Let me just introduce you to Dr. Murthy. He is from the School of Physics, not Department of Physics, but School of Physics, University of Hyderabad in India. Professor Murthy is also the coordinator of the academic affairs of the Center for Modeling, Simulation, and Design, MSc from that institution. Okay, he has many research interests. Okay, he's expert in many research areas. But very briefly, his research interests include Monte Carlo modeling in statistical physics, also Monte Carlo modeling in radiation transport, random walks, and many others. Professor Murthy has about 200 publications in reviewed, peer-reviewed journals and many other things. He has done his postdoctoral research in Indira Gandhi Center of Atomic Research in theoretical studies sections of the materials. So we have no more ado, so let's welcome back there.
Thank you very much for a very elaborate introduction. And I only wish that the prediction that you made, the talk will be interesting, come true. And let me say thanks for inviting me to this place. And how much time you have?
You can take it. We are not in this, we are not in this.
I'm going to talk about demons don't die. The origin for this talk comes from two considerations. Recently, people are talking about what we call as second law violating microstates. For a very long time, it was the theoreticians who were talking about second law violation, and you know, when a theoretician says something, nobody believes it, except himself. Whereas when an experimentalist announces a result, everyone believes it, except himself. Okay? So it was in the realm of theoreticians. But recently they have carried out some experiments with single protein molecule dragged through a viscous fluid, and they have actually observed second law violating scenarios. In fact, for a very long time, it was the policy of physical review letter that if any paper contains the word second law violation, you don't need to send it to the referee, it can be rejected right away. They made an exception to that, and there was a paper that came in physical review letter about 11 years ago. The title of the paper was Observation of Second Law Violating Microstates. So I got interested as when the paper was published, and subsequently a lot of work has been done. And surprisingly, it is my thesis, that surprisingly I found that what these people are talking about as second law violation or second law violating scenarios is something which Maxwell about 140 years ago said in the context of demon. That's what I'm going to call it. The demon is, actually I should call it strictly Maxwell's demons don't die. Okay? So I have removed the word Maxwell so to make that title very attractive. Okay. So my aim will be, if I'm able to show that the recent work that have come in the context of second law violating microstate, that it is actually equivalent to what Maxwell postulated in terms of a demon. What is the Maxwell's demon? Maxwell's demon is a creature which violates the second law. I can tell you that there are hundreds of ways of stating the second law. I will pick up a few of them. One of the standard statement of the second law of thermodynamics is that you cannot extract useful work from an equilibrium system. Or put it in another way, if you want to extract work from heat, you have to have two sources, one at a higher temperature, a sink at a lower temperature, and you should establish a flow of heat from higher temperature to lower temperature, and then if you are able to establish that gradient, then you will be able to extract work. If you have an equilibrium system, there are no temperature gradient, and hence you will not be able to extract work. If you are able to show through a Gedanken experiment, a thought experiment, because theoreticians are capable of only thought experiment, if you are able to show that the second law is violated, that will be a big thing. Then it gives a handle for the experimenters to how to translate that in terms of experiments. So what does the demand do? So I have imagine that I have a box full of gas at equilibrium. So the molecules, the gas is made up of molecules, and we are moving here and there. This is what I have a point.
Okay, ready?
Oh,
You can pass them on.
yeah, one.
I want it back.
So I have a gas in equilibrium, and imagine that the demon sets up a wall, and he has a door in the wall. What the demon does is, whenever a fast moving molecule tries to go from here to here, it opens the gate. In the same way, whenever a slow moving molecule tries to go from here to here, it opens the gate. The other way, he closes. That is, if there is a molecule which is moving very slowly, if it tries to pass through that, the demon will not permit. Let us say the demon operates for quite a bit of time, then you will find that all the fast moving molecules have accumulated here, all the slow moving molecules are accumulated here. We know from Maxwell's distribution, the temperature is higher here, lower here. Once you have established the temperature gradient, I can run a Carnot's engine and then extract work from that. So the demon helps you extract work from an equilibrium system. Of course, for a very long time, people did not understand what exactly Maxwell meant by that. What Maxwell said was, imagine what the demon does. It tries to establish a...
I mean, when this happens, the fast moving molecules are on one side and the slow moving on the other side, can we still call it an equilibrium system? I mean, is it still...
The whole idea is from the demon establishes a non-equilibrium, that is a temperature gradient in an equilibrium system. Once a temperature gradient is established, I can run a heat engine, extract work. Okay? Now, I'll come to that. I think you will find an answer in the sequence. Okay. So, what Maxwell exactly intended was that if you are going to have a statistical mechanical description of thermodynamics, what do we mean by that? For every thermodynamic quantity, for example energy, a thermodynamic energy that be represented by symbol U. How do I calculate this thermodynamic energy from the point from statistical mechanics? So I define a random variable called energy. Let me define it by a symbol E. The thermodynamic energy is the average of the random variable energy averaged over a suitable ensemble. It can be a canonical ensemble if it's a closed system. It can be a microcanonical ensemble if it's an isolated system, or grand canonical ensemble if it is an open system. So there are two stages involved. I should define what is known as an energy, that is a fluctuating quantity in statistical mechanics. When I average that energy over a suitable ensemble, I get an energy, and I am going to relate it to the thermodynamic energy. Keep this in mind. So Maxwell said that if energy is going to be a fluctuating quantity, is it possible for me to visualize that what the demon manages to achieve, can it occur as a consequence of very natural equilibrium fluctuations that are ever present in the system? Is it possible that the system, when it fluctuates from one microstate to another microstate to another microstate, is it possible for you to observe the system in one of those very rare microstates which has this temperature gradient? Essentially what I am saying is, if you are going to assume that I am going to have all these molecules spread around uniformly, filling up the molecules going here and there, because no molecule is stationary, just colliding with each other and moving there. Is it possible in the process of movement, it is possible that for a short time all the molecules, fast moving molecules are here and slow moving molecules are here. After all, that is one of the possible microstates in the scenario. Statistical mechanics doesn't prevent you from the system from being in that state. So his idea was that
K.P.N. May I raise an objection here?
no, sure.
You are assuming that the Maxwell's demon is a large guy. In reality, he is a
I'm
molecule.
coming to that. I'm coming to that.
He is being bombarded
Yeah.
with molecules, so he is going to be disoriented in no time.
Yeah, sure. I'm going to come. In fact, Bernoulli gave this explanation and then said that he killed the Maxwell's demon. Okay? So there have been a large number of scientists who have made attempts to kill the Maxwell's demon. My thesis is physicists now are not smart enough to kill the Maxwell's demon yet, and it lives on. Let me come to that. Okay. So this is what Maxwell's demon is. It is trying with. Is it possible that the demon state, what I am going to call it as all the molecules here and all the fast moving molecules on one side, slow moving molecules on the other side, let me call it as a demon state. Is it possible for the demon state to come out of statistical fluctuation? Thermodynamics, it's not that, but in statistical mechanical description of thermodynamics, there is a possibility. That's what Maxwell pointed out. So let me start with this preliminary ideas. Let us start with that. Maxwell demon lives on. It was born in the year 1867. It's 144 years old now, but it is very much alive and kicking. At least twice it was pronounced dead. First time it was pronounced dead by saying that the Maxwell's demon, if it has to identify a molecule coming and going, the trapdoor has to be extremely small. It should be able to see the molecules. In that case, the Maxwell's demon has to be an extremely tiny creature of the molecular size. If it is extremely tiny creature of the molecular size, then the demon himself is subjected to the thermal fluctuations. And hence how we can operate the door. If obviously if you have a shaking hand and if your hand is all the time shaking, you can't open the door. This was the explanation that was given, but something very similar to what Professor Ramarao was saying. Bernoulli wrote a paper and then killed the demon, and subsequently Zurich information theoretic way, he killed the demon again. I am not going to go into the details because that will take too much away. Demon is there are two big volumes that have come about Maxwell's demon. In fact, it's a topic for a full semester course. So I am not going to the details of how it was pronounced dead twice. As I said, the demon proved to be too smart for the physicists. It has challenged the best of the minds. Presently, physicists have given